In the Module 5 assignment, you're going to be using the properties of igneous rocks to help understand how they form and, in turn, the history of how they formed. In truth, geologists care about rocks not really for the rocks themselves, but because of their ability to tell us about the history of the Earth and how the Earth works. So let me give you a good example here. This is a picture of Yosemite Valley in the central Sierra Nevada mountains in kind of the eastern part of California. It's a part of Yosemite National Park. All of the rock you see here is granite. Granite forms when a magma chamber, that is molten rock below the surface, solidifies, and it does so very slowly. But here it is at the surface. Here all the rock you see as far as the eye can see is granite. So just by knowing that one thing, by knowing that one fact that this rock is made of granite and we know how granite forms, we can work out pretty extensively the history of what happened here. So let me do that very quickly on the bottom of this image. Let's say this was the surface of the Earth, and sometime in the past there was a magma chamber that formed, and I'm going to make little plus symbols here to indicate that this was molten and solidified to make granite. So it solidified below the surface. Presumably above the surface, in fact there's good evidence that this was the case, above the surface there were volcanoes erupting at the time too. It makes sense if you have a magma chamber below, some of that molten rock is going to trickle up to the surface and probably erupt in volcanoes, and there were at the time. But here's our granite. Here's the granite that formed below the surface. Now, the fact that it's above the surface, we know a number of things had to happen. First of all, there had to have been some uplift. This stuff had to have been moved vertically and then eroded. All of the volcanoes eroded away, making this the new surface. And here's Yosemite Valley today. So we know that granite had to form. There had to have been some melting process which formed the original molten rock. It had to solidify below the surface nice and slowly. And then there had to have been subsequent uplift and erosion to remove all of the stuff on the top. Just by knowing that one thing, what the rock is and how it forms, we can work out the bulk of the history of what happened here. So let's get into igneous rocks and look at their properties and see how they're useful. There's two main things we care about when looking at igneous rocks. The first one is composition, and that's what the rock is made out of. What minerals, and therefore what elements make up that rock. And there's two main categories that we care about. One are the light-colored rocks, such as seen here. We have a special geology-specific name for those. They're called felsic because the light-colored rocks are rich in feldspar and silica. Silica, which is chemically SiO2. These are light-colored minerals, and so the felsic, the light-colored rocks, tend to be rather light-colored. There is one notable exception here. This is obsidian. Although it is black, it is 99.999% silica. It has a very trace amount of dark-colored minerals such as magnetite, which make it dark. However, it is the vast majority of it is silica, so it can be considered a felsic rock too. The other category are the dark-colored rocks, such as shown here, dark gray or black, and these have a special geology-specific word, mafic, because they're rich in magnesium or iron, and the magnesium and iron tend to make them dark-colored. They also contain a fair amount of silica. Most rocks that you'll ever find on the surface are at least 50% silica, but these contain a fair bit more iron and magnesium, and they tend to dominate in the color. So why do we care? Remember, we're interested in not the rocks, but what they tell us about the history of the Earth and how and when they formed. In order to produce a dark-colored mafic rock, you have to have a melt, a source of material that's relatively rich in magnesium or iron. And those include the mantle or the lower part of the continental crust. So if you find a mafic igneous rock, that means you know the source of the melt was something iron-rich, probably the lower part of the continental crust or oceanic crust or the upper part of the mantle. If you find a light-colored igneous rock, that melt was really rich in silica and not so rich in iron and magnesium. So it probably was a melt of something of the upper part of the continental crust. This is a bit of an oversimplification, but roughly speaking, this sort of rule of thumb works. The composition tells you what melted. Dark colored source was probably the lower part of the crust, oceanic crust or mantle. Light color, the source of the melt, was probably melted continental crust. Let's talk about this. So let's take a look at the second important property of igneous rocks, which we refer to as texture. An important thing here, texture in geology is never whether or not the rock is rough or smooth. Texture does not refer to how it feels to your fingers. I can take any rough rock and polish it smooth, and I can take any smooth rock and break it up to be rough. Texture refers to the properties of the inside of the rock, specifically to the minerals within the rock, not the shape of the rock itself, but the shape, the size, the arrangement, etc. of the parts inside the rock. Okay, so in igneous rock, texture refers to the size and arrangement of the minerals within the rock. And what we're often concerned with is crystal size. So one example of texture is crystal size. How big are the mineral crystals, the mineral pieces within the rock? There are a number of possibilities where the mineral crystals are huge, enormous, like the size of a nickel or larger, or that they're just all big enough to see, or that the crystals are there and they're tiny, or that there are no mineral crystals at all. There are a number of scenarios, and they all have kind of special names, which you've read about in the textbook or in the lecture videos. But here's a few examples. Here's a picture of granite. And granite has minerals that are all roughly about the same size, from a pea or smaller, and I can see them all with the naked eye. They're big enough to see, and they're all about the same size. So that has a special name of phaneritic. Here's another example. This is obsidian. I guess I read on here this is granite. Obsidian is special in that it doesn't have mineral crystals at all. It's just one big mass, and so it gets a special texture name called glassy. There are other names like aphanitic. That's where the mineral crystals are there. They're just all very tiny and they're very hard to see. You need a high-powered hand lens or a microscope to see them. Another possibility with texture is whether or not the rock contains bubble holes. So this is pumice. And pumice is mostly air. It's full of holes where volcanic gas used to be, and that gas has escaped, leaving behind this sort of matrix around those bubbles. And so this has a special name for texture called vesicular. The vesicle is kind of the special geology name for those bubble holes. So in the last part, composition told us what melted, the source of the melt. Texture tells you how and where that melt cooled off and formed solid rock. Rocks that contain big mineral crystals, such as granite, and big here means that you can see it with the naked eye, those cooled off quite slowly. There was a lot of time for the atoms to kind of join their neighbors and form those mineral crystals and grow them over time. Rocks that cooled off very quickly, like in the case of obsidian, have very tiny crystals or none at all. If they have very, very tiny crystals, it's called aphanitic, or none at all in the case of obsidian, called glassy. There was no time for those atoms to join together and organize to make mineral crystals. In obsidian, it all cooled off essentially instantly into one solid mass. And in the case of pumice, this tells us about the history of cooling in that it had to form at the surface. It was full of bubble holes that used to be filled with volcanic gas, and those of course come out of that gas forms at erupting volcanoes, and so here we know both that obsidian and the pumice must have cooled off and formed solid rock at the surface, whereas granite must have cooled off and formed solid rock somewhere deep within the crust. All right, let's look at the assignment specifically. It looks a lot like the minerals lab. The first page has a number of general things and properties to write down to help you remember the important things of igneous rock, such as the definition, the two properties I just discussed, why they're important, and then a look at these two properties, just a little practice to think about the composition, and in the second case, the texture. So just to do some hypothetical looks at the various scenarios of light and dark rocks and large and small crystals before you actually get into the details. The next 2 pages of the lab look like this, where you're going to be looking at your igneous rocks in your rock and mineral collection and identifying some things such as their composition. Are they light colored or dark colored? What was therefore the source material? What does that tell you about what melted to make that rock? You're going to be looking at the texture and identifying the specific names, phaneritic, etc., and what that tells you about where it occurred. And here include a photo of your rock. I'd like to see a picture of each of your rocks so I can better understand what you're saying in these sections based on the rock that you're looking at. So you have 5 of these. At the end, the last page, like the minerals lab, I ask you to go outside and find some rocks that match these properties. Okay? The important thing is that you find rocks that match the composition and texture. Even if they're not igneous rocks, but they look like they might be and they match the properties identified here, that's fine. The important thing is not that you find the correct igneous rock, but you find a rock which matches these properties. And these are set up to make you think a little bit about what mafic really means or what a fast cooling lava means, etc. Take a picture of it, put them here, and some kind of piece of identifying information to show that you found that rock and you took that picture, such as take the picture of the rock next to your student ID. All right, that's the end. Please let me know if you have any questions.